Hi everyone, welcome back to on my YouTube channel again for the fifth lecture of PYQ series of distillation mass transfer. So here I'll be starting with 2016 GATE previous year paper. So you can see the question says that a binary distillation column is to be designed using McCabe method. The distillation contains 90 mole percent of more volatile component. So here distillate contains 90 mole percent of more volatile component. So let's try to write down the data that has been given in the problem. So 0.90 and Q line with the point of intersection of Q line with the equilibrium curve is this one. So when we talk about the McCabe diagram, you can see this looks like in this way. Okay, so here this one is the X and this one is the Y. So if you see there is a equilibrium curve something like that, and after that also you can see there is a Y equals to X line something like that. Okay, something. Okay, now when we see these things, that Q line is okay, so after that I'll be denoting this point XD on Y equals to X line. So this one is your XD and this point start with XD comma XD. This is the coordinate of this rectifying section equation line, and after that you can see the point of intersection of Q line with the equilibrium curve is 0.5 and 0.7. So let's say Q line will be something like that, and the point of intersection of Q line and equilibrium curve is something like that, and you are supposed to calculate the minimum reflux ratio. So in order to calculate the minimum reflux ratio, the rectifying section line, a stripping section line and the Q line should cut at equilibrium line, right? So this rectifying section line should pass through from this particular point, then only you will be able to calculate the minimum reflux ratio, right? And the coordinate of this point has been given to you, obviously 0.5 and 0.7. okay, so when we calculate the slope of rectifying section line, so that is equals to Rm divided by Rm plus 1, and that will be equals to how much? 0.90 minus 0.70 divided by 0.90 minus 0.60. So that is equals to 0.2 divided by 0.3, 2 by 3. So that will be equals to these things. Now you are supposed to calculate the minimum reflux ratio. So we can calculate now 3 Rm, that is equals to 2 Rm plus 2. So the value of Rm will be equals to 2. So the minimum reflux ratio value will be equals to 2 for this particular problem. This was very simple problem. Okay, so this one was very simple problem, but you can calculate this problem in this way. That is, you have to calculate the slope, and slope is R by R plus 1. But when it comes to crossing equilibrium line and Q line and the rectifying section line at equilibrium curve, then this will give you the minimum reflux ratio. Moving to the next problem, the question says that two packed towers are designed for the same mass velocity of the gas. So there are two packed tower. Let's say this one is first one, and again second one is this one. So vapor velocity, let's say assuming is V and P. The first has liquid and gas flow rate same mass flow velocity. So velocity is same, mass flow velocity is same, and the first and the second, first has liquid and vapor flow rate is 30 and 1.2. So let's say vapor flow rate is 1.2 kg per second here, while the corresponding flow rate in the second column is this one. So I am assuming that this one is V1 and vapor flow rate in second one is 1.8 kg per second, here kg per second. The ratio of design diameter of the wider tower to that of the narrower tower. So you have to calculate the diameter. So let's say I am assuming D1 is the diameter of this one, D2 is the diameter of these two. So if I want to calculate B1 will be equals to rho A1 V1, and again V2 is equals to rho A1 U1, and V2 is equals to rho A2 U2. Is that clear? And it has been given that U1 is equals to U2 in the problem, right? And V1 is given to you, V2 is given to you. So let's say I am assuming this one is equation first and equation second. Density of the vapor in both of these column is same. So you can calculate that if I'll divide V1 divided by V2, so I can write rho A1 U1 divided by rho A2 U2. So you can say rho 1 and rho 1 will get cancelled out. So again you can write V1 divided by V2, that is equals to A1 divided by A2 and again u1 divided by u2, and u1 and u2 is also same, it will get cancelled out. So v1 by v2, v1 is 1.2 and v2 is 1.8, so I can write 1.2 divided by 1.8, that is equals to again pi by 4 into d1 square divided by pi by 4 into d2 square. So this will get cancelled out. So d1 divided by d2, that is equals to 1.2 divided by 1.8 whole to the power 1 by 2, that is equals to 2 by 3 whole to the power 1 by 2, right? So you are supposed to calculate d2 divided by d1, that is equals to 1.5 whole to the power 1 by 2, that is equals to 1.225, something like that, right? So you are supposed to calculate the ratio of the diameter of the wider column to the top. So obviously if d2 is greater than d1, then definitely this value will be greater than 1, and ultimately you will be able to get this answer. So 1.225. Is that clear? Okay, so after that I'll be moving towards the next problem. The next problem says that a distillation column handling a binary mixture of A and B is operating at a total reflux condition, means R is tending to infinity. Total reflux condition means if a distillation column is looking something like that, and the liquid which is coming out here is completely returned back here. So here there is no distillate collected, right? All of the liquid that is coming here is taken back to the distillation column, something like that. If it is feed, and in the bottom of the distillation column you will see there it looks like something away. It has two ideal stages including the reboiler. So it has two ideal stages. So if I am talking about Nm plus 1, that is equals to 2, right? The mole fraction of more volatile component in the residue, so xw is given to use 0.1, the average relative volatility is given to 4, then the mole fraction of A in the distillate. So you are supposed to calculate xd is equals to what? So when we write this problem while using the Fensky equation, so in order to solve minimum number of stages required for distillation column, we use Fensky equation and we write Nm plus 1, that is equals to log xd upon 1 minus xd multiplied with 1 minus xw upon xw and divided by log of alpha. So Nm plus 1 is given as 2, that is equals to log xd you have to calculate, we don't know xd, 1 minus xd multiplied with xw is known to you, so that will be equals to 0.9 divided by 0.1 and divided by log of 4. So this equation is very simple now, so you can calculate 2 multiplied with log of 4, that is equals to log of 9 xd divided by 1 minus xd. So you can also write log 16, that is equals to log 9 xd divided by 1 minus xd. So log will get cancelled out, so you can write 16 is equals to 9 xd upon 1 minus xd. So you can write 16 minus 16 xd is equals to 9 xd. So 25 xd is equals to 16, so xd will be equals to 16 by 25, that will be equals to 0.64. So the mole fraction of more volatile component in the distillate will be equals to 0.64. Is that clear? This is very simple. This question was based on the Fensky equation, and you know the Fensky equation, it is used to calculate the minimum number of stages required in the distillation column, right? Okay, so I hope this question is clear to all of you. Now I'll be moving towards the next problem, and this problem has been asked in 2022. This is very important problem also, and this was a very theoretical question. The question says that a simple distillation column is designed to separate an ideal binary mixture to a specified distillate and bottom purities at a given column pressure. If RR minimum is the minimum reflux ratio for the separation, so calculate the statement that is not correct with regard to the variation in the total annualized cost TAC of the column with respect to reflux ratio. So here you can see, when we talk about this kind of problem in the distillation column, so you have to make this kind of curve. So this is the cost, let's say, and this is the reflux ratio. So obviously this particular things will start from minimum reflux ratio. So let's say RR minimum, right? So when we see RR minimum, so first you will see when reflux ratio is increased from minimum to at optimum condition, kind of that. Or if I am going to increase the reflux ratio, so what will happen? The boiler and reboiler cost and this condenser cost will increase, right? So first I'll tell you that the total cost that is decreasing. Why? Because if you will increase the reflux ratio, number of trays required will decrease, and if number of trays required is decreasing, then what will happen? The fixed cost cost first will decreasing. So fixed capital will go like that, and it will go like that, right? Because initially it will go and it will decrease, and when it will reaches to the minimum, optimum value, after that again what will happen, due to increase in diameter of the column, your fixed capital increasing. So if you will see, this is your fixed capital investment. Now when we talk about the operating capital, so operating capital will always increase, right? So let's say I have to shift this curve. So what I just wanted to discuss here, so fixed capital will go like that, operating capital will continuously increase. Now if you will club, let's say this one is fixed capital, this one is working capital investment, and now when we talk about the total capital investment, that will be equals to fixed capital investment plus working capital investment, right? So here you can see there is a steep decrease in and a steep increase in your fixed capital. So this is the R optimum. Once it will reaches to the R optimum, if you are increasing a reflux ratio more than that, the fixed capital cost will start increasing. And now if you want to plot these things, because this is the combination of both effect, that working capital investment and total capital investment, so it will go like that. So if I'll add both of these, so it will start like that, something like that, right? So here this one is the total capital investment, and at this point you can see this is the R optimum. So what you can see, that total annual cost has a minima with respect to RR, correct? The sharpest increase in TAC occurs as RR approaches to RR. No, that is wrong. So this one is wrong. The sharpest decrease in TAC occurs as RR approaches RR minimum. That is also wrong. There is sharpest decrease is not. You can see, you cannot see sharpest decrease. This is very smooth decrease. So this is also wrong. TAC increases with RR greater than RR minimum. No, first it is decreasing and after that it is increasing. So this is also wrong. So TAC has a minima with respect to the RR. So you can see that TAC will reach to a minima with respect to RR minimum. So R. So your option A will be your correct answer. So this is very good question, conceptual question, but again you have to understand the logic behind this question. But yes, so just try to think, if these kind of questions have been coming in the examination, you have to think a lot. Now coming to the next problem, the question says that an equimolar binary mixture is to be separated. So if I am talking about equimolar binary mixture, so XF feed composition of more volatile component I am assuming is XF is 0.5. The feed rate is 50. So feed rate is also given, that is your 50 kilomole per minute. The mole fraction of more volatile component in the top and bottom would be, so here XD is also given, that is 0.90, and XW is equals to 0.01. The feed as well as the reflux stream are saturated liquid. So feed and reflux stream are saturated liquid. If saturated liquid is there, then Q will be equals to 1. On the application of Mackay-Thiele method, the operating line Y is 1.5x minus 0.005. A stripping section line is this one. So this one is the stripping section line. So you are supposed to calculate the more volatile component. The reflux ratio is, so you are supposed to calculate what is R. Okay, great. So we know the value of Q. So when we talk about the stripping section equation slope, that is L bar by V bar, that is used to be equals to R plus Q into F by D divided by R plus 1 plus Q minus 1 into F by D. And how it is coming, so you can write L bar minus L divided by F, that is equals to Q, and obviously V minus V bar divided by F is equals to 1 minus Q. So I am clubbing both of these equations. I will be calculating L bar and I will be calculating V bar, and once I will divide L bar by V bar, you will be getting this equation. That is, this is very simple. If you don't remember, then you can calculate this equation from here only, right? Now here in this particular problem, you can say that stripping section equation line slope is given to you, that is 1.5. Means L bar by V bar is given to you is 1.5. R we are supposed to calculate, Q is 1, and F is given to you, that is 50, right? F is given to you 50 divided by D upon R, you don't know, R plus 1 plus Q minus 1. So Q is 1, so that will be equals to 0. Is that clear? So in this particular problem, you can say that 1.5, that is equals to R plus 50 divided by D divided by R plus 1. So here you are supposed to calculate D first. So you know F is equals to W plus D. This one is the equation first if overall balance is applied, and F into XF, that is equals to W into XW plus D into XD. So we are supposed to calculate the value of XD. So I can write here F is how much? F is given to you 50. I can write 50 multiplied with XF is also given. XF is 0.5. So that is equals to 0.5. That is equals to W can be written as 50 minus D. And again XW is also given to you. That is 0.01 plus D we don't know, and that is 0.9. Is that clear? So you can calculate this is 25, that is equals to 5 minus 0.01 D plus 0.9 D. So that can be written as 20, that is equals to 0.89 D. So the value of D can be written as 20 divided by 0.89. Once you have calculated the value of D, you can substitute this value here and you can calculate the value of R. So you can write 1 plus 5R plus 1.5, that is equals to R plus 50 divided by 20 multiplied with 0.89. Is that clear? So you can say that 0.5 R, that is equals to obviously 2.5 multiplied with 0.89 minus 1.5. The value of R can be written as 2.5 multiplied with 0.89 minus 1.5 divided by 0.5. So once you calculate these things, you will be able to get your answer here. Is that clear? Okay, I hope this one is clear to all of you. Now I'll be moving towards the next question, and this one is the last question asked in 2023. It's a really good question, but you have to understand this question. This is based on batch distillation or release distillation. The question says that distillation of a non-reactive binary mixture with component A and B is carried out on a batch still as shown in the figure below. The initial charge of the mixture in a still is 1 kilomole per hour. 1 kilomole. So F is given to you 1 mole, 1 kilomole. The initial and final amount of A in the still are, so if I am talking about initial moles of A, Na initial is 0.1 kilomole. So means what is mole fraction of A here? So X of feed in mole fraction, that is equals to 0.1, and the XW, that is 0.01. Is that clear? So directly I can write here F into XF, that is given as 0.1, and W into XW, that is given as 0.01, right? So use constant relative volatility. Alpha is also given, that is 4.5. The mole fraction of B remaining in the vessel is, you are supposed to calculate mole fraction of B in the remaining mixture. That means 1 minus XW is equals to what? Okay, so if I mean I'm not going to derive this formula again for the batch distillation, but again just in the previous lecture I have already derived this formula. So if I write ln F by W, that can be written as 0 to 1, or directly you can say alpha ln F into, sorry, this formula will be looking like that, sorry, ln F into XF divided by W into XW, that is equals to alpha ln F into 1 minus XF divided by W into 1 minus XW. This is just an analytical formula for batch distillation. So you can see F into XF and W into XW is given to you 0.1 and 0.01. So now I will directly substitute 0.1 divided by 0.01, that is alpha. Alpha is also given to you 4.5 and ln F into 1 minus XF. So F is given to you how much? F is 1. So total this one is 1. So F into XF is this one. So F into 1 minus XF will be equals to 0.9 directly. 1 minus 0.1. So directly you can write 0.9 divided by W minus W into XW. And W is also given to you how much? Or W into XW is 0.01, right? So from here I can write ln 0.1 divided by 0.01, that is equals to 4.5 ln 0.9 divided by w minus xw is given to you 0.09, right? From here, this equation will give you the value of w, right? Now once you know the value of w, once you know the value of w, so you know w into xw equals to 0.09. So you can calculate xw is equals to 0.09 divided by w, and you are supposed to calculate 1 minus xw, that is equals to 1 minus 0.09 divided by w. That's it. This will be your answer. So I mean, again, just you had to understand in this kind of problem, if you see this kind of problem, you have to understand what kind of parameter is given and what kind of things that is being asked in the question. That is very important thing. So some students will get confused in solving this question. They will calculate the value of w and directly they will tell the answer. No, that has not been asked. You are supposed to calculate the mole fraction of B in the bottom product, means in the these things in the still that is there remaining in the vessel, is that is 1 minus xw. Xw is mole fraction of more volatile component, right? That is A. 1 minus xw is mole fraction of another component, that is B, right? So that is all about the distillation previous year question. So I have completed the PYQ series of distillation. After that I'll be starting with humidification and drying, and then I'll go to membrane separation, and after that I'll be doing for the absorption. So I think continuously within 5 Feb I'll be able to complete the mass transfer and fluid mechanics PYQ series also. So what I'll say is you continuously watch this video. Definitely you are going to get lots of advantage from this particular problem, right? I'm also driving the concept that is being used in the previous year, so that there if you are going to forget the formula, then you will be able to drive the formula also. Okay, thank you all for attending the series. See you tomorrow.